Hey everyone, we're going to learn about projectile motion today. So take out your notebook and something to write with, and we'll start to take some notes. This first part, you don't really need to write anything, but once we get to the notes and the example problems, then feel free to stop the video at any time to take the necessary notes. So what we're going to do is we're going to start out by looking at horizontally launched projectiles. Scrolling down right here, we see that on the left hand side we have this ruler and this person is dropping a ball. We're going to use the scale of 1 centimeter is equal to 5 meters. And then we need to draw the positions of the dropped ball at 1 second intervals. And we're going to pretend that air drag or air resistance doesn't exist, and we're going to assume that the acceleration due to gravity g is 10 meters per second per second. We need to estimate the number of seconds the ball is in the air. So to do this, we need to use one of our kinematic equations, because as a ball is dropped, it's uniformly accelerated towards the ground because of gravity. And so if we're trying to figure out how far the ball falls each second, we have to use the second kinematic equation, which is displacement is equal to the initial velocity times time plus 1/2 times the acceleration due to gravity times time squared. But we can simplify this a little bit more, because if this ball is dropped, that means the initial velocity is actually 0, so that creates this whole term to be 0. So we're left with delta x, or the displacement, is equal to 1/2, and the acceleration due to gravity is, we're just going to put g in there, and that's multiplied by this time squared. So I'm actually going to draw these the ball in at every 1 second interval. So what we need to do is we need to plug 1 second into the equation and see where the ball is at 1 second. And then we do that for 2 seconds, and we keep going until the ball hits the ground. So I'm going to work this out here, and let's try this. So the displacement is 1/2 times 10 meters per second times 1 second squared. That would be the first displacement at t equals 1 would be 1 times 10 divided by 2, which would be 5 meters. That would mean at 1 second the ball is right there. So let's keep working these out. So the displacement is equal to 1/2 times 10 meters per second at 2 seconds squared. So simplifying this, we actually get one of these 2's is going to cancel out that 1/2. So we're left 2 times 10, which is 20 meters. And since 1 centimeter is equal to 5 meters, that means the ball is now going to be at 4 right here. And we can keep going. The displacement is equal to 1/2 times 10 times 3 squared. So t equals 3 that would be 9 times 10, which would be 90, and 1/2 of 90 is 45 meters. 45 divided by 5 is actually going to be 9. So we can see that the displacement of the ball is now increasing, and that's due to gravity. And let's try going one farther. So the displacement is equal to 1/2, and now our time is actually 4 seconds. So 10 times 4 squared. So the displacement at t is equal to 4 seconds is, 4 squared is 16 times 10, which would be 160, divided by 2, and that would be 80 meters. And if we divided 80 by 5, 5 will go into 80 16 times. So the ball is actually going to land right there. So if we're trying to estimate the amount of time that the ball is in the air for, well, if the ball hits the ground right at 16, we can count these. So this would be t is equal to 0, t is equal to 1 second, 2 seconds, 3 seconds, and 4 seconds. So the ball would be in the air for a total of 4 seconds. Now, so that is a free fall problem. That's what we've done already in the past. And now projectile motion also involves horizontal motion. So we're really just combining horizontal motion with vertical motion to create projectile motion. So this person right here, you can see that he's throwing this ball horizontally. And if there wasn't gravity at all, the ball would take a straight path and it would keep going straight at a constant velocity at the speed at which he threw the ball. However, if he's on Earth, gravity's going to start to act on it. So what we need to do is, I'm actually just going to read number 2. The 4 positions of the thrown ball with no gravity are at 1 second intervals. At 1 centimeter is equal to 5 meters, carefully draw the positions of the ball with gravity. Neglect air drag and assume that g is still 10 meters per second per second. Connect your positions with the smooth curve to show the path of the ball. How is the motion in the vertical direction affected by the motion in the horizontal direction? So basically what we want to do here is we've got the vertical motion on the left and the horizontal motion on the right. If we kind of draw these horizontal and vertical lines connecting the ball's position, we can actually see what the trajectory of the ball would look like. So let's give this a shot. I'm going to draw these in as dotted lines. First position would be right there. The next one would be right there at 3 seconds. The position of the projectile would be right there. And then the last one, well, we know that it's going to hit the ground, so we actually need to follow it all the way down. So now we can actually connect the dots here, but it should be with a smooth curve because projectiles take a parabolic arc for their trajectory. So I'm going to try my best to make this look like a parabola. Alright, there we go. So we just combined the horizontal and vertical motions to create projectile motion. And so the question is, how is the motion in the vertical direction affected by the motion in the horizontal direction? That's kind of a trick question because we just combined vertical motion with horizontal motion. They're actually completely independent of each other. So they aren't affected at all. So no effect. So if there's one thing to take away from this concept development, it is that horizontal motion and vertical motion are completely independent of each other. They do not affect each other in any way. Whenever you have a projectile, you can break down that motion into vertical motion, which is accelerated by gravity, and horizontal motion, which is not. It's going at a constant velocity as indicated up here. And we can see that those positions are equidistant away from each other. So the horizontal motion of that ball is a constant velocity, and it's always a constant velocity if we're not considering air resistance. And the vertical motion is accelerated by gravity. So to kind of back that up a little bit, what I've done is I've created a GIF from a video that I made in class, and just to kind of show you what the vertical motion and the horizontal motion look like for a volleyball going through the air. This GIF that I just created actually recently, it took a lot of work, but what I've done is I've placed these, overlaid these volleyballs at about every 6 frames. And what it's supposed to show you is that the motion for the volleyball in the X direction is completely independent for the motion in the Y direction. As you see the volleyballs at the bottom of the screen, that's marking the position of the ball horizontally every 6 frames. And hopefully you can see that the volleyballs are spaced equidistant apart or equally spaced apart, which shows that that ball is going at a constant velocity in the horizontal direction. The volleyballs to the right of the screen, you can see that they get closer at the top of its path, and then as the ball falls, the volleyballs actually get spread apart. And so what's happening there is that actually gravity is acting on the ball immediately, and so it's causing the ball to slow down, and when it gets to the top of its path, it's actually momentarily stopped vertically, but gravity is still acting on it, so acceleration due to gravity is still happening, and it's causing the ball to pick up speed back towards the ground. So the takeaway here is that the motion in the Y direction, the vertical motion, is completely independent to the constant velocity motion in the horizontal direction. Okay, so this is where I would like you to take your notes out and something to write with. To solve projectile motion problems, we need to break down the motion into its X direction and its Y direction. And the reason why we have to do this is because in the X direction or the horizontal direction, the equations are different than in the Y direction. And that's because in the X direction, it's constant velocity. In the Y direction, it's accelerated motion. So we're going to start with writing that down. So in the X direction, we saw from the GIF as well as the concept development that we just did. The X direction is constant velocity. And if the motion in the X direction is constant velocity, that means the acceleration in the X direction is 0 meters per second, which means there's no acceleration. And if that's the case, all of those equations that we just learned for free fall, we don't have to use them because those are for accelerated motion. And if we're just talking about constant velocity, the only equation that we have to worry about is the velocity equation. Velocity is equal to the change in position or the displacement divided by the change in time. And that's it in the X direction. So if this is the case, then all we need to know is we need to know 2 variables. And if we know 2 of those variables, we can plug those into the equation to find the other one. So now let's look at the Y direction. Okay, and since the Y direction has to do with gravity and acceleration due to gravity, gravity's causing the projectile to speed up and slow down. So that means we are talking about uniform accelerated motion. So uniformly accelerated motion. And we call this UAM. All right, so uniformly accelerated motion, we have to use the equations that we have already been exposed to. So I'm going to write them down right here again. If you have these down, I guess you don't need to write them, but it'd probably be good to have them all in one place. So the final velocity is equal to the initial velocity plus the acceleration times the change in time. The displacement equation, displacement is equal to the initial velocity times time plus 1/2 times acceleration times the change in time squared. The third equation is final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. And the last equation is the displacement is equal to 1/2 times final velocity plus the initial velocity times the change in time. And keep in mind, all of these variables are in the vertical direction. So if we see delta x or displacement, that is the vertical displacement, not the horizontal displacement. If we see acceleration, that's going to be g, or minus 9.8 or minus 10 meters per second okay? And one thing to note for these equations is that all of these variables in both equations are vectors with the exception of time. Time is the only scalar. And since time is the only scalar, we can use, if we figure out time, then we can plug it into either equation for horizontal motion or vertical motion. Because time does not have direction associated with it. We can use them in both. So we're gonna use that to help us solve these projectile motion problems. So let's get started on our first example of a horizontally launched projectile. We are ready to start an example problem for horizontally launched projectiles. So go ahead and pause the video so you can copy down the problem itself, as well as draw a diagram for the problem. So to start, here's the example. Carl runs off a 6-meter tall cliff with an initial velocity of 10 meters per second. We want to figure out how long does it take until Carl reaches the water, and then for B, how far horizontally did Carl travel before splashing into the water. To start these problems off, what we need to do is we need to practice our problem solving skills by listing out our variables that we know and that we don't know. The twist here is unlike projectile motion, or unlike free fall problems, we have horizontal and vertical motion here. So we need to decipher between those types of motion as well as those variables. So what I would like you to do is to copy these variables down, similar to the problems that we've done in the past for free fall. We list out all the variables, and then we'll break apart the problem, identifying what we know and then what we don't know, and then we can solve accordingly. So let's break apart this problem right here. So Carl runs off the cliff, and the cliff is 6 meters tall. So if the cliff is 6 meters tall, that means if Carl's jumping off the top of the cliff, he's going to fall 6 meters. So that is actually our vertical displacement. That is our delta x in the y direction, so our vertical displacement. And that is 6 meters. But he actually falls 6 meters because his displacement from the base of the cliff is actually decreasing, so we're going to call it a minus 6 meters. The next piece of information that we're given is that Carl has an initial velocity of 10 meters per second. So if he's running off this cliff, all of his motion is in the horizontal direction. So that is the initial velocity in the x direction, and that is 10 meters per second. And that seems like that's all that we're given, but that's really not the case. Remember that a projectile motion problem combines the motion in the x direction as well as the y direction. A free fall problem combined with a constant velocity problem. So if we think about free fall, and if we think about the motion in just the y direction, we know that the acceleration is going to be constant, and that acceleration is g, the acceleration due to gravity. And it is minus 10 meters per second each second. And on top of that, if all of Carl's motion is in the x direction, and the moment that he steps off of the cliff, he's going to be immediately accelerated towards the water. But his initial velocity in just the y direction is actually 0 meters per second. It's just like dropping a ball off the edge of the cliff. So his initial velocity in the y direction is 0 meters per second. So we know 3 of these variables. That means we can find out, if we need to, the final velocity in the y direction, or the speed at which he hits the water, as well as the time it takes for him to hit the water. And since time is a scalar, once we figure out time, we can plug it into the horizontal equation, and then we can figure out how far away from the cliff he landed. So let's figure these out. We need to figure out how long until Carl reaches the water. So how much time does it take for him to hit the water? So what we need to do is we need to pick an equation that has time but does not have final velocity. Well, let's look up here. What's one of our equations that has time but does not have final velocity? I think that's our displacement curve. Okay. So that's our delta x is equal to the initial velocity times time plus 1/2 times the acceleration times time squared. So this is our equation 2. The initial velocity times time plus 1/2 times the acceleration times time squared. And since in the y direction the velocity is 0, we can get rid of this whole term, and what we're left with is the displacement in the y direction is equal to 1/2 times the acceleration due to gravity times the square of the time. So all we need to do here is plug in our numbers and then figure out what t is equal to. So I'm going to solve for t, which is delta x in the y direction multiplied by 2 is equal to gt squared. If I divide both sides by g, then we get t squared by itself. 2 times delta x y divided by g is equal to t squared. So that means time is equal to the square root of 2 times the vertical displacement divided by g. So let's go ahead and plug these values in. We get 2 times the vertical displacement, which is minus 6 meters, all over minus 10 meters per second. So we can see that those negative signs cancel, and what we're left with is 2 times 6, which is 12, divided by 10. So we get time of square root of 1.2. So let's plug that into the calculator. And we get the time it takes for Carl to hit the water is equal to 1.1 seconds. So now, since we figured out how much time it takes Carl to hit the water, we can actually take the time and plug that into the velocity equation to figure out how far away horizontally Carl traveled before splashing into the water. So we know that horizontal motion is velocity is equal to the horizontal displacement divided by the change in time. So we know that the time is equal to 1.1 seconds, and we know that the initial velocity is equal to 10 meters per second. So let's rearrange this equation to solve for the range or the horizontal displacement. So that is delta x is equal to initial velocity times time. So we get 10 meters per second times 1.1 seconds. So we get the total range to be 11 total meters. Okay, so what this means is that the moment Carl left the top of the cliff, it took him 1.1 seconds to fall and hit the water, and then we used that time to figure out how far away he landed away from the base of the cliff, which is 11 meters. So that's what we need to do to solve these problems, is we need to break the motion into its x direction and the y direction. We need to identify those variables, identify what we know and what we don't know, and then figure out a way, the easiest way, maybe it's starting with horizontal motion, maybe it's starting with vertical motion, but what you need to do is find a way to figure out the time first before you can solve anything else, because time is the only variable that you can use in either forms of motion, because it's the only scalar that we're dealing with. All right, that wraps everything up. Feel free to contact me if you have any questions. Take it easy.